So now in this video we have a DIY voltage booster. It's not a terribly great voltage booster, but there you can see 5 series LEDs lighting up, even though we're only using 3 volts right there. You'll see them better if we turn the lights off. So if you really need a voltage booster, you just use a voltage booster module, but this shows that we can actually build one with common components. I can't press and release the switch fast enough for this monostable 555 timer, so we wired up some pulse circuitry. We have a small value capacitor that's only 100 picofarad going to the trigger, pin 2 of the 555 timer, and there's also a 10K resistor on each side of the capacitor going to the positive supply. So this is a pull-up resistor. It holds 5 volts at pin 2 until I press the switch, and then we got a connection to ground, but only briefly because the capacitor starts charging and goes up to 5 volts. But during that brief period where it's low, that sets the output high and this capacitor starts charging. So this has to get high before this capacitor gets to 2/3 supply voltage. And so you hold the switch, that charges the 5, you have that. When you release the switch, then the capacitor can discharge through those 2 resistors. When we get that low pulse to pin 2, the trigger pin, the capacitor starts charging. As I said, when it gets to 2/3 supply voltage, as you can see right there, to pin 6, then the output goes low and the capacitor discharges instantly through 7. We're only using 0.47 microfarad capacitor here, so it's charging really quick. If this gets to 2/3 supply voltage though, and you still have a low input, less than 1/3 of the supply voltage to pin 2, pin 2 is more powerful. It won't let it discharge. The capacitor will just keep charging and the output will stay high. That's why we have to get pin 2 high as soon as possible, quicker than I can press and release the switch. And as always, we have to power the integrated circuit, pin number 8, VCC, to the positive supply, pin number 1, the negative supply, right there, ground, and then you can see pin 4 goes to the positive supply as well. That's just because if we give it a low input, connect it close to ground, the output will be low and will stay low no matter what. That's what reset means. So keeping it to the positive supply prevents it from doing anything. The output has a fairly low value resistor right there, 1K. Lower might even work better, but in any case, that's going to the base of the NPN bipolar junction transistor. I'm using a 2N2222. You can see pin 3 there, 100 or 1000 ohm resistor to the middle pin base of the 2N2222. The collector side, all we have is this coil right here, going to the positive supply from the collector. Oh, also, and the diode, which is right back here, connected to that same row. We'll get to that in a little bit. But in any case, the coil is a 10 millihenry coil. A higher value coil would probably work out better. It also has 25 ohms of resistance based on how much current flows through it. And so if you had one with a lower resistance, that would work better as well. But this is pretty much the best I got. So when we get that low pulse to the trigger pin, that sets the output high. You get a little base to emitter current, and the coil here starts conducting. Doesn't conduct instantly, but conducts pretty quickly. That's important. We have to get it conducting long enough that it's conducting fully. And then when the output drops back to low, there will be ground on both sides. We cut base to emitter current. That stops the transistor from conducting. That's where the diode comes in. So since it can't go through the transistor, the coil still wants to conduct for a brief period of time. It's going to force current. It'll fry the transistor if we're not careful. So we have the diode here. It will pump current into the capacitor using a 100 microfarad capacitor. And also there's the LEDs. If the voltage is high enough, current will flow through the LEDs. And so that pumps it. Capacitor voltage goes up each time you pump current into it. So now the LEDs give a nice visual effect right there. As you can see, it takes a while to pump up the voltage enough to get them to light up, and it's still probably a bit below 12 volts to really light up green LEDs, 5 of them in series. you would need more than 15 volts, but they start letting a little current flow through, and they light up a little bit at lower voltages. When I use a 555 timer, which we will do in the next video to make it even faster, we'll just use another 555 timer wired in an A-stable mode. Then when the LEDs get pretty bright, I measure the voltage across the resistor, and because it's a 1 kilo ohm resistor, it's really easy. If there's 1 volt across it, 1 milliamp of current is flowing through it. If there's plus the LEDs. If there's 2 volts across it, then 2 milliamps of current is flowing through that whole circuit. And I couldn't even get it to 1 volt. I got close. And so in any case, we pump the current into the capacitor. When you have the diode, make sure you put it in the right way. The cathode is the side with the band, and then the anode is the side without the band. Again, if current doesn't flow through that diode, voltage is going to build up, and it's going to fry whatever it forces current through, probably the transistor. So we got to make sure current can flow to ground one way or another. The capacitor, I think this has a 50 volt limit, much more than what we're using here now. But if we get rid of the LEDs, sooner or later, that's going to just keep pumping current into the capacitor. The voltage is going to get too high for the capacitor, and it will blow. So a lot of times I put like a Zener diode parallel to it, but in this video, these LEDs are our Zener diode. As long as they light up, I know current's flowing through them, and the voltage isn't building up too much across the capacitor. So now I hooked up the oscilloscope to measure the capacitor. The negative side of the capacitor is to the negative rail, and that's where the other alligator clip is connected there. So we're measuring this voltage difference, 0 volts here, and then each square here is 2 volts. So we got 2, 4, 6, and right now about 7 volts. The voltage is dropping this quickly because this oscilloscope only has about 1 million ohms of resistance. So to get more accurate voltage readings, you want multimeters with, or oscilloscopes I mean, with a higher impedance. And when you measure voltage, multimeters need a higher impedance as well. But in any case, there you can see, as I hit the button, I think during this period I wasn't getting a proper connection. These switches don't love breadboards. When they're brand new, they'll pop out of the breadboard. But there you can see it rises, and so we got 2, 4, 6, 8, 10. Looks like somewhere around 11 the LEDs start glowing. Since there's 5 of them in series and they are green, each one of them has a forward voltage of about 3 volts approximately. So to get really bright, we need about 15 volts total. But at lower voltages, current will flow. So that's just with the power supply at only 3 volts right there. We go to 5, and I added this right here, which is connected to ground, so I can short the capacitor. Now you can see it's up to 5. Probably a little bit less because we got that diode drop, but it should go quicker because we're getting more current through the inductor due to the higher voltage, so it's going to pump more current into the capacitor. But again, the LEDs are basically a Zener diode. They're going to make it really hard for the voltage to rise any further once current starts going through them. But you see they got brighter. So in any case, hopefully you enjoyed. This was a long video. Next video we're going to use a 555 timer. So instead of me hitting the switch, the 555 timer is going to be given high, low, rapid pulses. We're going to make it A-stable mode. But I'm going to keep the pulse circuitry because I can't really time the high and lows perfectly to try to make sure that the inductor conducts fully but then shuts off before it's just wasting current by conducting through the transistor longer than it needs to.